Hey everyone, today we're going to be talking about the dot product. Namely, we're going to be talking about what it is, how to calculate it, some important results, and its applications, right? So why are we even calculating the dot product in the first place? Next week, I'm going to be doing a video on the cross product, and the reason why I'm doing this series is because I wanted to tackle a really interesting vector identity in my video after that. So if those are already up, the links to them will be on the screen and in the description. And if they're not up yet, then be sure to subscribe so that you don't miss it. So let's start by talking about the intuitive definition of what the dot product is. The dot product is one way that we can multiply two vectors, and it gives us a measure of how much the two vectors point in the same direction. It's worth noting that the dot product gives us a scalar, so we give it two vectors and it gives us a number, and that number tells us how aligned they are relative to their length. So let's talk about how we would compute it in Cartesian coordinates. Let's say that this vector is a, and it goes along a distance ax in the x direction and a sub y in the y direction. We'll call this vector b, and say it goes along bx in the x direction and b sub y in the y direction. So our dot product, a dot b, is given by our two x coordinates multiplied together, added to our two y coordinates multiplied together. Notice again that we're giving in two vectors and we're getting out one number. So why does this fit our definition? If we were to imagine sliding a along towards the right, notice that they would be getting closer to being in the same direction. Also, our a sub x value would be increasing, which would mean that our entire dot product is increasing. So as our vectors get closer to pointing in the same direction, our dot product will increase. When we talk about how aligned two things are, a natural thought might be to consider the angle between them. If we're dealing with two vectors that are directly in a line, it's pretty natural to say that we want the dot product to be at a maximum there. Remember that the dot product is a measure of how aligned they are, scaled to their magnitudes. Then the angle between them, which we'll call theta, is equal to 0. And then we'll want the dot product to be equal to the magnitude of a times the magnitude of b. What happens when the two vectors are perpendicular? Well then, the angle between them is going to be equal to pi on 2. The dot product measures how in line two vectors are. If they're perpendicular, then they're not pointing in the same direction at all. They're as far away from each other as they can be. So in this case, the dot product is going to be equal to 0. The last case we'll consider is when they are pointing in opposite directions, or the angle between them is equal to pi. Here, they're still pointing in the same direction, but they're just opposite of each other. So we'll want the dot product to be equal to the negative magnitude of a times the magnitude of b. If we're trying to come up with a general case, right? So not just for these specific angles, but any angle in between, you might look at it and notice, so we're starting at 1 when the angle is 0. At pi on 2, we're going to 0. And then at pi, it reaches -1. This might look familiar because this is just a cosine curve. So in general, we're going to say that a dot b is equal to the magnitude of a times the magnitude of b times the cosine of the angle between them. So far we have two different definitions for the dot product. One works when we're talking about angles, and the other is when we're talking about Cartesian positions. It turns out, of course, that these two things are equal. We can prove this using the law of cosines. I've done the setup here, but I'm going to leave the actual proof to you. So we've talked a little bit about what the dot product is and how to calculate it, but before we get into the applications, I want to give you some main takeaways, or some important things to remember. Now this first one we've actually talked a little bit about, but it's such an important point that I'm going to re-emphasize it here. If you take the vector a and dot it with the vector b, and the result is 0. That is equivalent to saying that a and b are orthogonal, or perpendicular. Another important thing to note is that if you take a vector and dot it with itself, you're going to get the magnitude of that vector squared. The next thing I want to talk about is how we can generalize this into 3 dimensions or even higher. If we have a 3-dimensional vector, it's going to have an x component, a y component, and a z component. And we can dot that with another vector. And just like before, we're going to start by multiplying the two x terms. Then we multiply the two y terms. And now, since we're in 3 dimensions, we also need to add the multiple of the two z terms. Lastly, I want to talk about how we can find the angle between two vectors using the dot product. We defined a dot b as equal to the magnitude of the first times the magnitude of the second times the cosine of the angle between them. Well, if we divide both sides by the two magnitudes, and then take cosine inverse on both sides, we're left with the angle between the two vectors. I wanted to leave this video talking about a couple of applications of the dot product, and we're going to start by talking about physics. The first one that you're likely to run into is the calculation for work. So let's say we apply some force on an object, but it moves in a different direction. Now, how would we find the work done by this force? Well, you can sort of think of it as we want to find how much of the force is going in the delta r direction, and, as we've talked about, that's just as easy as calculating F dot delta r. Another application in physics of the dot product is in quantum mechanics. In quantum mechanics, you're actually working with a more general version of the dot product, and that's called an inner product. If you've seen this notation, that's essentially what it represents, is an inner product. Another common place you'll see dot products is in linear algebra a lot, and linear algebra is one of the most important areas in math when it comes to applications. If you're talking about matrices, a really important subset of them has this property of orthogonality, which basically means the columns of the matrix are orthogonal. Now, we're not going to get too much into this, but orthogonality is really important, and as we've shown before, you can show orthogonality using the dot product. Another place the dot product is really important is when you're looking at projections. So let's say I have some line and I have some point. How am I going to project the point onto the line? Well, to project it with the least error, we're going to do it orthogonal to the line. In this case, we're projecting one point onto a line, but you also might project a point onto a plane. Dot products actually build the foundation for us to be able to do more complex things, like projecting points onto planes, or maybe even lines onto planes, etc. Another use case for the dot product is when you're working with weighted sums. If you look at the first formula for dot products that we looked at, let's say we have some vector a, and we're dotting it with another vector w. If we expand that out, it's going to be a1 times w1 plus a2 times w2, and this goes on and on and on until, we eventually reach however many dimensions this vector is in. And you can kind of see that this acts as a weighted sum. So w1 would be the weight of the first component, w2 would be the weight of the second, and this ends up being really important if you're looking in machine learning, and neural networks use a lot of weighted sums. And that's essentially the foundations for how neural networks work. So, dot products are incredibly important in a lot of different applications. If you don't want to miss my video on the cross product, be sure to subscribe. If you enjoyed the video, give it a like, and if you have any questions or spotted any mistakes, feel free to leave a comment. Thanks for watching.